I'll find it and post it. I don't see it. Okay. Yeah.
Could you go over the 3 laws of thermodynamics and how we need to relate them to like what's going to be on the test?
Let's just walk through it. What's the first law of thermodynamics? There is no thermodynamics. Just kidding. Okay. That joke is not going to work in like 10 years, I guarantee it. Okay. First law is right? Is that the first law from the notes? I don't know. Yeah. How are you gonna, do you think this is gonna relate to the exam? Yeah. Okay, we've talked about that. What's the second law? From the notes, you're gonna have to remind me. Have something to do with entropy always increasing, something like that? Right? Is that the second law? Is that what I... Yeah? Okay, good. And? Greater than 0, except for what special case? Right? Okay. So we talked about the second law? Yeah, lots, right? Lots today during class. Third law? I heard someone say add 0k. I think that's the third law, isn't it? Yeah. And it just tells you that you can calculate absolute entropies, right? And you can't calculate absolute delta H's or absolute delta G's. So we've talked about all of these 3 things. Now I'm not just going to tell you or ask you, tell me about the first law, But it's helpful, if you want to be sort of schooled in the art, it's good to remember first law, second law, third law. But mostly we've really just focused on how to use these concepts. Honestly, I don't care if you know that this is the third law or not. Doesn't matter. What I want you to know is that delta S0 is 0 at 0k for a perfect crystal. I don't care if you know that this is the first law or not. You just need to know that this equation is true and how to use it. Yeah?
Why can delta S of the universe be not 0? How can that? I don't understand that.
Delta S of the universe being
greater than 0.
Greater than 0?
Yeah.
So, in an irreversible process, so it's called a law because that's how it is. But in an irreversible process, delta S being greater than 0 describes the energy penalty for doing that work. So it tells you that you can't recover all the energy in both directions from an irreversible process. So every time you perform an irreversible process, you have to give some energy away, right? How much energy do you have to give away? What's the units on delta S? Joules per K. So the energy that you have to give away corresponds to the temperature at which you perform that reaction. So if you want to make ammonia, you have to give some energy up that you can never ever get back. It's gone. It went to the universe. I don't know where the universe keeps it, but you'll never get it back. But for phase change, for melting water, for boiling water, you can get back that phase change energy perfectly. It's a reversible process. So you can go all day long with the phase change and put energy in, get the same energy out. Put energy in, get the same energy out. All day long. But if you wanted to take 3H2 plus 2 plus N2, every time you go this way, you have to give some energy. Every time you go that way, you have to give away more energy. Back and forth. And so you lose the entropy every single time you do that reaction. Yeah?
So we can look up in a table, it's delta S and find a number, but we have like gaseous water into liquid water in a table, just say 0.
Oh, we don't have any tables for delta S of the universe. What do we have tables for? Delta S 0, what does this refer to? System, right? Reactions. Things that go on inside the box. We need to use, what do we know for the entropy of the system? How do we calculate that? Q over T. So we need to make these two calculations if we want to figure out a quantity for delta S of the universe. It's easy to know whether it's positive or 0, but if we want to figure this out, we need to figure out delta S0 and we need to figure out Q over T, and then we can make the sum. Go ahead.
So that's why I was pulling apart the first point that Q and W are not really the same thing, because that kind of validates the second law in that you can't directly interchange between them, and that's where the S of the universe is always increasing.
Oh, interesting. Yeah, I understand that. So what Tom is saying is that when you convert from Q to W, you do irreversible. It's an irreversible process in lots of instances, so you lose some entropy.
Right,
Yeah.
so the delta S of the universe is always going up.
You'll run into it again in your third year. Don't worry about it for now. Go ahead.
This might not be like relative to what we're doing, but if, say like a reaction gives off energy and it's lost to the universe, how is it fair to say that energy is not created or destroyed if that energy is lost forever, say from Earth, and then we get energy from the sun to replace it, but the sun is not technically an endless resource. So since we don't understand how, like, the extent of the universe, then how can we determine that?
Yeah. So I know what you're saying, and so in that, remember when we're talking about the universe and we're talking about the system and the surroundings, you always need to draw this box, right? So where do you want to put the sun? We can put it in the surroundings if we want, right? What does the sun do? Pumps heat into the system. What's the system? Earth. Right? Okay, there's Europe over there. I'm North American. I draw, North and South America facing, right? Okay, so what's the sign of Q in the way I've drawn this thing? Positive, right? Okay, so when we do work, what happens? So what was the next part? So we do work here,
well,
right?
I understand that, but my question is, I guess, how can they make it apply to the entire universe if we don't understand the extent?
Yeah, so this...
Once the sun dies and there's no more heat to create life on Earth, then how do we... Then this would basically be ended. Like, this law would be ended.
Well, no. So remember, what's the universe here? It's everything, right? So it's all the way around. So this, you can never get around. So this is just a mathematical definition. Entropy is not something that you can hold in your hand. Entropy is just defined by this equation. So you don't have to go in and, figure out these tricky situations. Oh, if the sun dies and this and that, it doesn't matter. The only thing you need to know about the entropy of the universe is this. So I don't know whether this corresponds to, you know, whatever. It doesn't matter. In the context of thermodynamics, this is what we need to know. And so remember, the entropy of the sun, it goes other places, right? The universe is a big place. And so the disorder, what this is saying is that the disorder is always increasing in the universe. And I think that that's true. So don't worry, this will work for anything, but drawing this system surrounding when you get to these big things is very difficult. If we just stick with chemical reactions and phase changes, we'll get through it here. Yes?
Doesn't the second law also mean that heat always doesn't go from cold, doesn't flow from cold to hot? The heat always flows from hot to cold.
Yeah, so there are ramifications of the second law, just like Tom said, the interconversion between heat and work, the flow of heat from hot to cold. You know, those are all things that happen because of this, but that's more advanced stuff. Other questions? Yes?
Are we gonna, spontaneous reactions wasn't like on the study guide, but I think we talked about it in the notes. Should we just like...
What is a spontaneous reaction? What's the condition? Or a thermodynamically favorable reaction? Delta G is less than 0 for thermo. I don't like to call it a spontaneous reaction because that might tell you that it happens instantly, right? Spontaneous. What spontaneous is that it will happen at some point. We just don't know when. So I don't want to confuse spontaneous with happens right away. I want to say thermodynamically favorable. So next year I'll correct that in the notes. Okay, more questions? All right, see you on Thursday. Feel free to call, make an appointment, all of that stuff. I'm happy to chat. And don't forget to bring your homework on Thursday. Oh, the homework.